Students, welcome to Sunil's tutorial. I'm Sunil Mirwani and today we'll be doing this chapter called as magnetic effect of electric current. Let's see this. Last time we had seen suspended type galvanometer. Today we'll see another one which is called as pivoted coil type galvanometer, moving coil galvanometer. Let's see the diagram, guys. First, all of you draw the diagram. Let's see this. These are your permanent magnets. Now let's try to understand this. This is your pivoted coil type moving coil galvanometer. Now in this, the coil is pivoted between two pole pieces. This is your coil. These are your coil. They are pivoted between two pole pieces by the means of two springs. Here's that spring right in the center. Right, one from below, the other from above. The current enters the coil through one spring and leaves the coil through the other spring. Right. The springs help to bring the coil back to its original position. There is a long pointer which is attached to the coil which helps to read the angle of rotation, and the entire apparatus is kept in a glass container. Very simple, very straightforward construction. Right? Can you just write this construction down? You want me to explain again? You have, okay, I'll just write it down and show it to you. So the coil is pivoted between the pole piece of a magnet by means of two spiral springs, one from below and the other from above. Okay, the current enters the coil through one spring and leaves the coil to the other. So this is your spring. The coil is pivoted in the center with the help of the spring, right? Two springs are holding that coil there. Okay, let's move on ahead, and the current is going to enter and leave the coil through the spring, right? The springs help to bring the coil back to its original position once the current stops to flow. Springs bring the coils back to its original position once the current stops to flow. Right? So here you have that's your mechanism to bring the coil back to its original position, and you have a long pointer attached to the coil. A long pointer is attached to the coil, and it reads the angle of rotation of the coil on the scale. It reads the angle of rotation of the coil on a scale. So that's the construction of a pivoted coil type moving coil galvanometer. Now let us try to understand the forces or the working of a galvanometer. First, let's try to understand the working of a moving coil galvanometer. Let's consider a suspended coil type moving type galvanometer. I'm just going to show you the forces that are going to be acting in this. Guys, can you see this? Now, you have coil here. This is the coil. Just show you a few turns of the coil. And you have the spring attached over here. And you have the wire bringing in this here. Right? This is your north pole of the magnet. This is the south pole of the magnet. You have, due to this magnet, there is a magnetic induction which I'm going to show you. Let's change the color to show you magnetic induction. Let's consider that there is a constant magnetic field B because of the north and the south pole of the magnet. This is that constant magnetic field B due to the north and the south pole of the magnet. Right, this is your magnetic induction B. Okay. Now, let's see what are the forces that are going to act on the coil and why does it behave the way it does. Right? Q, R, S and P. Let's consider the four vertices of the coil. Right? Now, let's start. Consider a rectangular coil PQRS. This is your rectangular coil PQRS of length L and breadth B. L is the length of the coil, B is the breadth of the coil, right? Suspended in a magnetic induction, in a magnetic field of induction B. Suspended in a magnetic field of induction B, right? So that's your basic construction. Now let's try to find out the forces that are going to be acting here. Now initially the plane of the coil is parallel to the field. This is your plane of the coil. It is parallel to the magnetic field. Guys, see this. The plane of the coil is straight. The field is also straight. So I can say that initially the plane of the coil is parallel to the field. Right? Now you have, guys, can you see this? You have two sides. Let's consider the shorter sides. The shorter sides PS and QR, the shorter sides PS and QR are parallel to the direction of the field. Since they are parallel to the direction of the field, they will not experience any force. However, the sides QR and the sides PQ and SR are perpendicular to the direction of the field. Hence, they will experience a force which will have a magnitude BIL. Since they are perpendicular to the direction of the field, the force that they will experience is going to be BIL. So this is going to experience a force in this direction, and this is going to experience a force in this direction. This is going to be the force that is going to be experienced by these two sides. Why is this going to experience a force? Because it is perpendicular to the direction of the magnetic field. Do you understand this? These two sides, the shorter sides will not experience a force because they are parallel. The longer sides will experience a force because they are perpendicular to the direction of the magnetic field. Can you write this down, please? The short sides PS and QR are parallel to the direction of the field. Hence, they do not experience any force. However, sides PQ and SR are perpendicular to the direction of the field. And hence they experience a force F of magnitude BIL. This is the force that is going to be experienced by the two sides. Right? Now, according to Fleming's left-hand rule, this force acting on side PQ is going to be directed outwards. Right? If I apply Fleming's left-hand rule, the force is always directed outwards. So on PQ, it is going to be directed outwards. That means it is going to be in this direction. Similarly, on SR also it is going to be directed on the other side. So that I can, if I am calling this as outward, I will call that as inward. So here the force is directed in outward direction. Here the force is directed in inward direction. The force is equal in magnitude. The magnitude of which is BIL. It is opposite in direction. Now if there are two forces which are equal in magnitude and opposite in direction, they give rise to torque. They are separated by a distance of PQ, so they will give rise to torque. Fine, do we get this thing clear? That's how torque is produced here. Fine, let's write this down. According to Fleming's left-hand rule, this force F acting on side PQ is directed outwards, while the force F acting on side SR is directed inwards and perpendicular to the plane. Now since you have these two forces are equal in magnitude and opposite in direction. These two forces are equal in magnitude and opposite in direction. Act at a distance. The distance between the two forces is going to be the breadth of the rectangle B, acting at a distance B apart, right? Hence, these forces form a couple. These forces form a couple. Fine, do we get this in here? So in that case, I can find out torque. If they are forming a couple, I can find out the torque. Torque is given by the formula 1 force into perpendicular distance between the two forces. 1 force into perpendicular distance between forces, right? One force is F, perpendicular distance between the forces is B, but F is nothing but BIL into B. So this is BIL into B, but length into breadth is nothing but area. Length of the rectangle into breadth of the rectangle will give you the area of the rectangle. Therefore, the torque that is going to be acting is going to be BIA, right? And it is this torque that makes the coil move. Thus the coil rotates under the action of this torque. Thus, the coil rotates under the action of this torque. Right? Now, this was in the case of suspended coil type moving coil galvanometer. What happens in the case of a pivoted galvanometer? I'll show you that here only. Now, I'll just draw the diagram first. This is your north pole, south pole. You have a center. Now you would have magnetic field that would be acting. Now the magnetic field that is going to be acting is going to be radial in nature. So you will have a radial magnetic field acting which is going to pass through the center. Right? This is going to be my radial magnetic field due to the magnets that is going to be acting on this, right? Let's assume that the total distance, let's consider this total distance to be say AD. This point is A, this point is D, right? Let's consider that total distance AD to be say, let's assume that length is B. Okay. Now what are the forces that are going to be acting here? Let's try to find out the forces acting on a pivoted coil moving coil galvanometer. Now in a coil galvanometer, I can say that the concave pieces produce a radial magnetic field. This is your radial magnetic field. Instead of producing the straight magnetic field, you are going to have a radial magnetic field. Produce a radial magnetic field right now if they are producing a radial magnetic field, the radial magnetic field is always going to be parallel to the plane of the direction of magnetic field. I can say that in any position, guys, can we just compare that with this? In the case of a rectangular field, only when the plane was only in this particular direction would the plane of the coil and the magnetic field be parallel. But in the case of a radial magnetic field, it would be parallel in all directions. I can say that at any position, in any position of the coil, in any position of the coil, it remains plane parallel with the direction of the magnetic field. It is that your coil. In any position of the coil, it remains plane parallel to the direction of the magnetic field. Fine, do we get this in clear? Now, hence I can say that the deflecting torque has the same constant magnitude in any position of the coil. There it had, in the case of a rectangular field, it had that torque of PIA only when it was in parallel position. Here it was always going to be in parallel position. So however the coil rotates, there is going to be a uniform magnetic field in any position of the coil. So I can say that hence the deflecting torque has the same constant magnitude BIA in any position of the coil. Because in all the position, the coil is always going to be parallel to that radial magnetic field, right? Now, due to the rotation of the coil, the suspension fiber gets twisted. Remember, we had done the diagram where you had a suspension fiber above and suspension fiber below. Due to the rotation of the coil, the suspension fiber gets twisted, right? And on account of elasticity, it will exert a torque which will be called as the restoring torque, and on account of elasticity, it will exert a torque called restoring torque. This is going to be the torque that is going to be exerted by the suspension fiber, right? The torque increases with the angle of the twist, and hence the opposite, the direction opposite, that is your deflecting torque, will also increase. The torque increases with the angle of twist, and its direction is opposite to that of the deflecting torque, and its direction is opposite to that of deflecting torque. Right? Hence for any angle of deflection, the deflecting torque will be equal to the restoring torque, because the deflection torque is going to be produced by the current that is flowing through the coil, and an equal and opposite amount of torque is going to be produced by the twist of the suspension fiber, right? So I can therefore say that hence for any angle of deflection, say let us assume theta, any angle of deflection theta, the magnitude of the torque is equal to that of the restoring torque, right? In which case I can therefore say that the restoring torque is equal to k theta, where I can say k is the restoring torque per unit angle of twist, right? So thus when the coil comes at rest, the deflecting torque will become equal to the restoring torque. Initially, as the current flows through the coil, it is going to produce a deflecting torque, right? At a certain point of time, this deflecting torque is going to be resisted by the elasticity of the suspension fiber. At a particular point, the coil comes to rest. At that particular position, the deflecting torque will be equal to the restoring torque. Current flows through the coil, which causes a torque. That torque will not go on forever. Why? Because there is a suspension fiber there that is going to oppose the movement of the coil. And at a particular point of time, for a particular current, the deflecting torque will become equal to the restoring torque. Right? Can we write this down? Thus, when the coil comes to rest, the deflecting torque is equal to the restoring torque. Deflecting torque for n number of turns, is going to be nothing but n into BIA. Restoring torque we said is k theta. Thus I is equal to k n b a theta, where k, n, b and a are constant. Therefore I can say that current is directly proportional to theta. Thus the angle of deflection of a moving coil galvanometer is directly proportional to the current flowing through the coil, and this is the principle on which a moving coil galvanometer works. Fine, do we get this thing clear? Now that I have a galvanometer ready, let us see how do I make an ammeter from it. What is an ammeter? An ammeter is an instrument that is used to measure current. Let's see the working of an ammeter. First of all, what is ammeter? It is an instrument used for measurement of current. Instrument used for measurement of current. Fine. Now, let's see how do I make an ammeter. Now, an ammeter is nothing but it is a moving coil galvanometer which has been designed to measure current in a circuit. Now, to measure current in a circuit, the galvanometer has to be connected in series, because it is only in the series that current remains constant. Ammeter has to measure current in the circuit. To measure current, it has to be connected in series. Now, if it is going to be connected in series, it is going to introduce a resistance of its own in the circuit, which will, due to this, some amount of current is going to get reduced, as a result of which the current that will be measured by the galvanometer will not be the actual current flowing through the circuit. In order to make sure that the current measured by the galvanometer is equal to the actual current in the circuit, I have to keep the resistance of galvanometer as low as possible. See guys, suppose if I have a circuit, this is my circuit, battery, some current I is flowing through the circuit, okay, this is the current. I want to find out what is the current I flowing through the circuit, okay. In order to do that, I want to measure current, that means I'll have to introduce galvanometer in series. So the same circuit again with the galvanometer introduced in series. Same voltage, same current I and same resistance R. Now the galvanometer has some internal resistance. Therefore, the total resistance of the circuit will change. If the total resistance of the circuit changes, by Ohm's law we know V is equal to IR. V remaining constant, V is equal to IR guys. V remaining constant, if the value of R increases, then the value of I will decrease. That means the current that will be measured by the galvanometer will be equal to the current flowing through the external circuit plus the current flowing through the galvanometer. That means that will not be the actual current that is flowing through the external circuit. In order to find out how much current is flowing through the external circuit, I should make sure that the resistance of this galvanometer is almost negligible. Only if the resistance of the galvanometer is almost negligible will it be able to measure the current in the circuit. Do you understand what is an ammeter and how do I have to connect an ammeter? So do you understand this? So in order to measure current in a circuit, I have to make sure that the resistance of the galvanometer is very small. Even if a small current is passed through the galvanometer, it should give you a deflection, and the coil in the galvanometer is very delicate and it gets easily damaged. So I should make sure that a large current should not flow through the coil of the galvanometer. Suppose if there is a very large current flowing through this, now the coil of the galvanometer is made up of thin wire. If a very large current flows through that coil, the coil could get burnt. So I have to protect my instrument, I have to make sure that the instrument is sensitive, and 3, I have to make sure that the instrument does not affect the actual, gives me the actual reading of the circuit. 3 things, 3 conditions I require from an ammeter. First, I have to make sure that the resistance is as low as possible so that I can measure the actual current. Second, I have to make sure that large current does not flow through the coil of the galvanometer. And third, even for a small current, the galvanometer should give me a proper deflection, right? In order to fulfill all these conditions, how do I, or what should I do so that a galvanometer can act as an ammeter? To fulfill these conditions, what you should do is connect a resistance of very large value in parallel with the galvanometer. First, let me just write the condition, then I'll show you how I convert a galvanometer into an ammeter. Conditions required from an ammeter. First, the resistance of the galvanometer must be very small. Second, small current passed through the galvanometer should give full scale deflection. Should give full scale deflection. Third, as the coil of galvanometer is very delicate. It can be easily damaged. Easily damaged. Hence, it can be easily damaged if large current flows through the coil. Flows through the coil. These are the reasons why a galvanometer cannot be used as it is as an ammeter. Right? Now, what is the modification? To fulfill all these conditions, a low value resistance must be connected in parallel with the coil of the galvanometer. To fulfill all the above conditions, a low value resistance must be connected in parallel with the coil of the galvanometer. Right? That means now your circuit, this is how your ammeter would be. You would have a galvanometer here and you would have a low value resistance in parallel with it. And this would be your ammeter. Right? Now, as current enters, let's assume that you have current I entering point A. It is going to be divided into two parts. One will be Ig and one will be, say, let's call this as S. This particular resistance is called as shunt resistance. So the current is going to be divided into two parts. Some part of the current is going to move through the galvanometer and some of it is going to move through the shunt resistance, and then the current comes back at point B and goes through the circuit. Fine, do we get this thing here? Now, since the value of shunt resistance is very low, most of the current will flow through the shunt resistance, thereby protecting the coil of the galvanometer, right? So this is how you have a galvanometer converted into an ammeter. Fine. So galvanometer, such a small value of resistor is called as shunt resistor. So you need to connect a shunt in parallel, right? Thus, a galvanometer is converted into an ammeter. Galvanometer is converted into an ammeter. Fine, do we get this thing clear? So that's how you convert a galvanometer into an ammeter, right? Okay, we'll stop this here for the day. We'll see the derivation of ammeter in the next lecture, right? Thank you very much.